Hey guys, today we are looking at notes for 7.1, which is all about simplifying, multiplying, and dividing rational expressions. So first and foremost, looking at little definitions here in box 1. So a rational expression is a fraction. We know ratio, rational means fraction. And then an expression can be a polynomial, which is in the numerator or the denominator. Could be just a number, it could be a variable, it could be a mixture of those two things. But we've got a fraction that's got some stuff on top and bottom that are not just numbers. So a rational expression is just that. For us to consider it being simplified, for a rational expression to be in simplified form, just means that there can't be any common factors between the numerator and the denominator. So just like a simplified fraction with just numbers, it reduces as far as possible. Anything that's in common between top and bottom just has to be reduced. So if we had variables in common, like if in this case both c were being multiplied by a and b on top and bottom, they would reduce because there's a common c on top and bottom. My simplified form would be a over b. We've seen these when we were dealing with fractions before. If we had 15 over 65, both of those are divisible by 5, so I could factor them out and reduce by 5 on both top and bottom, leaving me with 3 over 13. Now, in this last one, this is closer to what we'll see. We're starting to deal with some expressions on both top and bottom. In this case, they're already factored out for us. We didn't need to do that factoring. But we can see on both top and bottom here, my numerator and my denominator have this parenthesis in common that has x plus 3 inside. So because that parenthesis was on both top and bottom, it canceled out and reduced away. So we were able to reduce that and just be left with 4 over x plus 5. So when we're going through and simplifying, we've got 4 basic steps that we're going to do. The one that we just took a look at was already factored for us. That's not always going to be the case. So when we're starting with a problem that we're asked to simplify, our first step is going to be factoring it out, because we have to see if there are any common factors between the numerator and the denominator. So in order for us to check to see if anything can reduce, we needed to have those factors. And you're just going to do this one at a time. It doesn't matter what order you go in. We can factor out the numerator and then factor out the denominator, or vice versa. It's up to you. There's no rhyme or reason as to which we need to factor first. So if we take a look at the expression that we're given here in box 2, x squared minus 4x minus 12, all over x squared minus 4. Both of those are factorable using pretty normal methods. Up top, my leading coefficient is just 1. So I'm trying to figure out, if I'm trying to factor that, I'm trying to figure out what two numbers multiply together to give me negative 12, but add up to a negative 4. So once you look at the possibilities of the factors that give you negative 12, but add up to negative 4, you should come to the conclusion that x minus 6 and x plus 2 is how that numerator factors out, because negative 6 times 2 is negative 12, but negative 6 plus 2 is negative 4. My denominator here, x squared minus 4, depending on, again, how you view things and how you like to factor out these, we should recognize that as a binomial. The only way we know how to factor out a binomial is with a GCF, which there isn't one between x squared and negative 4. And the only option we have is using our difference of two squares. Both x squared and 4 are both perfect squares, which means this factors out into x plus 2, x minus 2. Because it always factors out into whatever that square root is of 4 in this case, with one plus in between, one minus in between. So we've got it factored completely. Step 2 is to reduce. So just like we did over in box 1, we're going to take a look and see if or what is common between my numerator and my denominator. In this case, my x plus 2 is on both top and bottom, so I can reduce that away. And then we're going to go ahead and rewrite it without those terms in my expression. So after I've canceled out my x plus 2, up top, all I'm left with is x minus 6. And all I'm left with underneath is x minus 2. And that's my final simplification for that expression. I know it's really tempting for us to reduce those x's away, but again, we have to kind of imagine this, that my x and my negative 6, or my x and my 6 are attached to each other with subtraction, and the same thing down below with my x and my minus 2. I can't just cancel and reduce away because it's not just multiplication. That's why we have to have it factored into those separate parentheses up in step 1, so that we can cancel out, because we can only reduce when it's multiplication. Now, something else that pops up here, something else that we have to take into account, is that when we cancel stuff out from our denominator, it eliminates some different restrictions that my graph would have created. In my denominator, we know that I can't have a denominator of 0. We know that that's not something we can do. It's just dividing by 0, and we're not allowed to have that. So what we need to do is make sure that anything that got canceled out from my denominator that could have been a possibility originally to start with to give me 0 is taken into account. So to figure out what our restrictions are, we're going to go ahead and set any of our canceled factors equal to 0. And then solve. So that'll tell me any values that, if I had originally plugged them into my beginning problem, would have given me a 0 in the denominator, and was not something that could have been an option for an x value when I started my problem. Because we're trying to simplify here, but we're trying to maintain everything still being true. So like in this case, my parenthesis that got canceled out up in box 1, or up in step 1 for box 2, I canceled out an x plus 2. So this x plus 2 that I canceled out, if I set that equal to 0, I'm going to go ahead and just solve. That tells me that -2 was originally a restricted value. So if I plugged -2 into my original problem, it would have given me a 0 in my denominator, which if I look back at what I started with, that makes sense. -2 squared is 4. 4 minus 4 is 0. But if I plug that -2 into my problem that I have simplified, -2 minus 2 is -4, and that's fine. So that's why we have to take that into account. The way that we'll write this up, once you've identified what that restricted value is, in my answer, I'll just add in here and say, hey, this is my simplified answer, but x cannot be -2. Because -2 is that restricted value that would have made my original problem 0 in the denominator. And that then is my final answer. I have to include both of those things. Again, we only do that if there are things that were in my denominator to start with that are not in my denominator at the end. So in this case, x plus 2 was in my denominator. It's not any longer. That's why x plus 2 equal to 0 gives me my restricted value. So as we go through the rest of these problems, we'll still have to kind of simplify at the end. So we'll get some more practice in that, and it'll get more familiar too as we work through them. In box 3, we're now working on multiplying rational expressions. So we know that when we multiply fractions, we multiply just straight across, and that's the same thing here for our rational expressions. It doesn't matter that it's got numbers and variables mixed together, I'm still just multiplying straight across. So when you're multiplying straight across with something like number 1, when it's all just different bases and exponents, we don't have any additions or subtractions, we've got 2 different ways that we can do this. And it's really a personal preference. It's the same thing that I say when I'm simplifying just 2 regular fractions. If I was going to multiply 5 over 2 times 6 over 10, you could, if you wanted to, multiply straight across and get 30 over 20 and then reduce it. Or what I usually do, I'll kind of reduce as I'm multiplying together. I can see that 5 and 10 will reduce this to a 1 and a 2. This 2 and this 6 will reduce it to a 3 and a 1. And then I combine them together at the end. So the same applies here with rational expressions. You can simplify and kind of reduce stuff as you go through and multiply your 2 fractions together, because we know at the end anything that was up top is going to end up top. Anything that was in my denominator is going to stay in my denominator, just combined together. So let's just, for this sake, for this method, let's go ahead and do multiply straight across, get it all as one thing, and then work on simplifying afterwards. So for number 1, if we're going to multiply straight across, coefficient times coefficient, 5 times 6 is 30. For my x values, x squared times x to the first gives me x cubed. And then I just had that single y squared, so it's still going to be there. Down below, 2 times 10 is 20. X is just the 1, so x y squared times y is y cubed. So now that I have it as just a single numerator, single denominator, I can go ahead and reduce however you prefer doing this. When I'm looking at my coefficients, like I can see that they're both just divisible by 10. I can kind of just cross out those zeros. 30 over 20 is going to reduce to 3 over 2. And then depending on whether you are thinking about this as kind of just reducing and canceling what's in common between top and bottom, or if you're going to quotient rule, where you're doing your top exponent minus your bottom exponent, is going to differ. Whichever method you're going to choose to do, go ahead and do that. I can see in this case, up top I have 3 x's, x cubed, and I have 1 down in my denominator, so one of them is going to cancel out, leave me with x squared up top. For my y values, I started with 2 up top and 3 in my denominator, so that means 2 of them are common between top and bottom, leave me with just 1 1 y value in my denominator. So simplified all the way down, up top I'm left with 3x squared, down below I'm left with 2y. 3x squared over 2y. Now, I still have to look to see if I have any restricted values. So if anything started in my denominator that is not there any longer, needs to be accounted for. So in this case, I had x in my denominator to start with. It is not in my denominator at the end. So I need to list that as a restricted value. That's not really anything I need to set equal to 0 to solve, because it was just x. So we would just say x cannot be 0. Oops. And that gives us our restricted value, because that was the thing that was canceled out, just x. So x cannot be 0. With number 2 in box 3, again, we're multiplying. In this case, a little bit different because now I've got expressions here, not just individual terms. So this is where I kind of use my preferred method. I'm not going to multiply these together and get into some big nasty polynomial before I try and factor it back out to cancel out what's in common. So what I'm going to do here, just like we did for box number 2, I'm going to go ahead and factor everything out as far as I can first. So up top on my first fraction, they've got a 3x in common. That gives me 3x times 1 minus x. If I just take a GCF out. In my denominator, x squared plus 4x minus 5. I'm trying to figure out what two things multiply to give me negative 5, but add up to a positive 4, which would be positive 5 and negative 1. In my second fraction, x squared plus x squared plus x minus 20, positive 5 and negative 4 add up to 1, but multiply to get negative 20. And then down below, 3x is just 3x. There's nothing that we can do with that. So that's factored out as far as I can go. So just starting to cancel what's in common. 3x and 3x show up in both numerator and denominator. X plus 5 is common. Now these terms over top of each other here, my 1 minus x and my x minus 1, is really, really tempting to just cancel them out as they are. They both have the same terms. They're both subtraction, but the order of them makes that not possible, because I need it to be x minus 1 on both top and bottom, or 1 minus x on both top and bottom, in order for it to be canceled out. So what I can do here is something we haven't had to do before. If I wanted to, because right now this is a positive 1 and a negative x up top. If I wanted to be a positive x and a negative 1, something I'm allowed to do is factor a negative 1 out of this, and that gives me negative 1 plus x up top, which is just the switched around version of x minus 1. So now that I have that, I can cancel out my negative 1 plus x and my x minus 1, since those are both negative 1 and positive x. So all I'm left with, after I do all of that canceling out there in red, I've got a negative 1, or just negative, and I have x minus 4 up top. Everything was eliminated from my denominator. All of the things that were originally down there are not there anymore. So, besides distributing my negative, which I should also do, switch colors here, my negative x plus 4 is my final expression. I'm going to have 3 different restricted values for this solution. Now, some of us and most of us, as we go along, will probably start being able to identify these restricted values without having to show our work for it, because it's really like solving those quadratics back in chapter 2, where each of these parentheses, if we just set them equal to 0, it always just gives me the opposite of what I see. So my restricted values here would be that x can't be -5, it can't be +1, and it can't be 0. Because I had 3 things, 1, 2, 3, that were eliminated from my denominator. So x plus 5 equals 0 would give me my -5. X minus 1 equals 0 would give me +1. And then 3x equals 0 would give me 0. So that's my solution. Negative x plus 4 is my expression with those 3 restricted values of -5, +1, and 0. All right, last but not least, number 3 in box 4. This is division. We know when we're dividing fractions, it's the same thing as just multiplying by the reciprocal. So the nice thing here for dividing these rational expressions, it's really just flipping over our second fraction, and then it's multiplication like we just did. So I'm not going to do these as separate steps. I'm going to kind of multitask and kill 2 birds with 1 stone. I'm going to factor out, just like I did in number 2 that we just finished up. I'm going to factor it as I flip. So in this first fraction, 4x does not factor out at all. It's just 4x. In my denominator, 5x and -20 have a 5 in common, leaving me with x minus 4. Since I'm dividing, I have to flip my second fraction over here. So when I factor this, the factored out version of my numerator is going to become my new denominator, and vice versa. So my numerator here, once I change this to multiplication, will be the factored form of x squared minus 6x plus 8. So we're looking for what multiplies together to give me positive 8. That adds up to -6, which means they are both negative. So -2 and -4 multiply together to give me 8, but add up to a -6. And then my numerator in the original problem, x squared minus 2x. When I factor that out, they have just a GCF of x in common, but that ends up being my denominator. Because again, I'm multiplying by the reciprocal. So these are going to get flipped over, which is why they end up being upside down once I turn it to multiplication. But now that I've done that, I've got it factored out. It's multiplication. I can just look at what's in common between numerator and denominator. So here, my x minus 4s cancel out. My x minus 2s cancel out. And my x's cancel out. So basically all my variable terms go away. I'm just left with 4 over 5. So restricted value wise, I've got 3 of them once again, 3 terms canceled out. I have restricted values. Let me zoom out so you can see still. We've got restricted values of 4, because x minus 4 equals 0 would give me positive 4. My x that got canceled out is just a 0. And then x minus 2 getting canceled out tells me that 2 was also a restricted value. So not in any particular order that those have to be in, but as long as you have all of your restricted values, that's all that really matters. So that is all for our notes for 7.1. Your homework for this section that we'll work on tomorrow is page 380 and 381, 4 through 32, every other even. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and let me know. Otherwise, have a fantastic day. We'll see you soon.